The paper I'm going to present today is called Deep Learning on a Data Diet, Finding Important Examples Early in Training. And this paper is published on NUS 2021.
All right.
And the authors are from Stanford and a senior research scientist from Google Brain.
So still working on the optimization landscape on, just look at the research interest, the first author. So have you investigated the other works of the first author?
Yeah, I think one is about the lost landscape, but
All right.
I didn't look
It's
at
not, it's not relevant to our classification landscape.
no.
All right, let's keep going on.
So today I want to start with some questions. The first one is, what is the role of data in machine learning? Because currently some researchers think data is much more important than the model architecture itself. And the second question is, which samples are important for generalization and how to find them? And for example, like those important samples stable or vary across different initializations and across different model architectures. If those important samples do exist, then how early in the training process can we identify them? So basically, it's about the problem is about prone data set. So we want to find a subset of original data set such that when model trained on the subset, it can perform as great as well as the model trained on the all data set.
So before Xianglin further proceed, so anyone will try to have to provide some answers about the role of data ML. So anyone would like to volunteer to answer this kind of question before Xianglin choose the solutions or reference solutions in the next few slides. So anyone would like to volunteer to try to answer the questions? Okay, could you please?
Yeah, recently I like literally yesterday I attended a workshop about densification. So in classification problems, usually clusters arise, right? So we have some clusters, and based on clusters, like later in latent space, we identify the class. So maybe the important samples are the ones which define the boundary of that cluster. It's like not precisely very, proxy of that class, but define the kind of boundary between the classes.
Okay, so Kusha, in summary, Kusha mentioned that the importance of the classifications, the importance of the training data for some task like classification is more like on how much these samples can define the boundary instead of how representative for a group of data, right? And anyone else will try to share your own views and what is the most, how do you define the importance of the training data? And also, what is the role of data ML? So this sounds like a simple questions, but maybe different people will have their more sophisticated interpretations about the role of the data. Rofan, what do you think about the importance of the data? What do you think about it?
I think important data should consider the representativeness and the diversity.
Okay, so maybe I share my personal point of view. So suppose we have 1 million data So a lot of the data might have redundant information, right? The overall, you can consider the model is basically a way of compress a large number of data into a generalizable information reference, which allow to facilitate the generalizable inference. So if we are able to learn the data with a smaller set of data, it doesn't bother for us to learn on a large number of data, let alone that's noisy. Sometimes the data set is very noisy, and it will introduce some training inefficiencies for the ML models. So if we can address the problems with a smaller number of data, we don't bother to look into a large number of data. So it's just more about information comprehension, the information compression efficiency. And as for Kush's points that the proxy or the boundaries, I think it is both concepts can fall into a problem of representativeness. And how do we define the representativeness? And how do we define the informativeness? As long as we have a way to measure the informativeness of each samples, we might have a way, just Xianglin showed it here, to prune the data set. And as long as the prune data set can achieve the same effect to learn a model, we believe that maybe the problem of a pruning data set is kind of optimization problems. We pick up the most informative samples from the training data to achieve the same learning effectiveness. Okay, let's keep going on.
Yeah, so the related work on prone data set. The first one is core set selection problem. Basically, you wanted to select a subset of training data that is very diverse and can mimic the true distribution. And the other related work, invent forgetting. Actually, this is a paper from ICLR in, I think, 2018, but in the next few slides, we would talk about it. And this paper is highly related to this paper, invent forgetting.
Okay.
So the invent forgetting, that paper is called an empirical study of example forgetting during deep neural network learning. Basically, they found that some samples will be forget in the training process. And by forget, I mean in the early training stage, the samples can be correctly classified, but in the late training stage, those samples would be wrongly classified. So this is what I meant by forget.
So here the term forget is to forget about the pre-trained data, or forget about it's not for pre-training. It's still for the normal training.
Yeah, you train it from scratch.
And the event here means samples, or
yeah, this forgetting event means some samples will be forget in the training process.
But for the epochs, when we define an epoch, it means that for each epoch, the model will see every sample in the training data, right? And if each training sample will be seen in each epoch, how could the model forget it? The point is, let me repeat. And the definition of epoch is that the model can train or pass every samples in the training data set, right? So, and we train the model epochs by epoch, right? And which means that for each sample, the model will see it in every epoch. You understand this?
Yeah.
So the question is, if a sample will be seen by the model in every epoch, and how could the model forget it?
But this is the truth. They do found some samples will be forget.
So it's not about forgetting, it's about ignoring or neglecting, right? So the model sees it, but it neglected it. And I think the idea is kind of different from forgetting event. Forgetting is that I didn't see you for a long time, I forget it. And ignoring means that I see you every day, but you didn't leave me any impression. I think kind of different, right?
But in the early training stage, those samples are correctly classified.
Maybe by chance,
Not by chance.
maybe accidentally, they're accidentally correct. And after training for a while,
Yeah, so they
are
do.
sacrificed.
They have evaluated this in the in the experiment part. So they have a random. So I think they, based on my memory, the chance of a sample being forget. So they use the random as the baseline, but those forgetting samples are much.
So I'm not sure whether the term forget is correct because the model still see the samples in every epoch, right? So this, but
Yeah,
it just means they fit it first and then forget it.
They're very likely to fit it by chance in the first area.
So I wanted to ask, so how does it happen? Is it like gradient is 0 in the samples?
Oh, sorry?
So Kush is asking how this event can happen. Why the model so maybe one of the my answer is that there's conflicting data. Suppose the model has limited expressiveness. So some samples will have to be sacrificed to for the model to fit the most samples, other samples. But that is just one example. But I just feel that the problem is more like a sacrifice or ignorance instead of forgetting some samples. And it's just a discussion of the terminology they use. So you can just keep going on. Yeah.
They have two findings. The first one is those forgetting samples are consistent across different architectures. That means, for example, you use CIFAR10 dataset and you train it over like VGG16, ResNet 18, ResNet 34 or other architecture. However, those forgetting samples are consistent.
So it basically means that it's the nature of a data set instead of the nature of the architecture.
Correct. And they also did another experiment by deleting them and retrain the model, and they found that there's, I wouldn't say without any impact on the test accuracy, but only sacrifice a little.
So it's more like it's more like irrelevant, ignorable, right? Ignorable samples, or those samples have very small Shapley value, so we can interpret this like this, right? Okay. So the idea is that we want to select those ignorable samples and prune them away. So is that that is idea of this paper, right?
This paper, you mean
or
the empirical study or the paper we are presenting today?
Whatever. So what is the goal? What is about
the empirical study of example for getting this paper only investigate like this forgetting event, and these two findings are their conclusion.
There's no surprise, right? So we know that some of the samples have to be sacrificed, and also the terminology of forget worries me a little bit. All right. So where this paper published, this empirical study?
The ICLR
2018. So okay, 4 years ago. Okay.
And in their paper, in order to find those forgotten samples, they need statistics throughout the whole training process, right? And they provide an example. When you train the CIFAR10 on ResNet 18 for 200 epochs, and the Spearman rank correlation between early and late score is good about 25 epochs. That means when you train the ResNet for 25 epochs and then find some forgotten samples. And those samples has a good correlation when you train.
And here I have to ask, what is the correlation? How do you calculate the statics, and what is the measurement to calculate the correlation? And how do you measure the statistics?
So when you train it for 25 epochs, you can get a forgotten score for each samples.
And how do we calculate the forgotten score?
Forgotten score, that means if the sample are not forgotten, then it's 0. If it's forgotten, then it's 1, I guess. And then you have a score. And when you train the ResNet over 200 epochs, you again can get a score.
For each samples have 200 scores.
I think 1 score. It's either forgotten or not.
So if each sample have only 1 score, how do you calculate the correlation? The correlation need to calculate two groups of data, right?
Mm.
And how do you calculate that?
Mm.
And then what do you mean by good of 25 epochs and stabilized? So which means that the score will have a trend, right?
Mm.
And this score is for the whole training data set or for individual training sample?
The score should be, no, here it means the Spearman rank correlation is good.
Yeah, I'm asking about the targeted data. The data, how do we define the scores? And how do we calculate the correlation?
I forgot about the details, but here this example wanted to say that we don't need to train the CPATEN for 200 epoch in order to find those forgetting samples. You can the score is stabilized after 75 epochs. So this is about the efficiency problem, because the paper we are going to present today wanted to answer how early in the training process can we identify them. But in this empirical study, they need 200 epochs, right? So
but the point is that we are still not clear how do they calculate the forgotten score, right? So for me, it is more like a Shapley value. Calculate the Shapley value for each training samples through some empirical approach, right? But up until now, we haven't got any clue how they calculate it. And if this paper is just for
two possibilities. One is the samples either be forgot or not, so it's either 1 or 0. The second possibility is they calculate how many times through the training process is a sample be forgot. So it might be forgot several times. Then they just
but for the problem, we want the model, the final version model, right? So we don't need the partially trained model. We need the final trained model. Suppose the model is trained well. And in the approach, we also want to know the answer before the training, right? If we want the technique to be useful, for example, the problem is that suppose we have a training data set of 50K samples, but because of the problem, for example, because of visualization problems, we only can visualize maybe 5K data on the canvas. So we want to pick up the most representative and important 5K, right, before the training, instead of after trainings, we finally pick up. We don't want that. So how could we do that, and how these correlations can help us?
so
yeah, we're not this time we're not prone the model, right? We prone the data set. And we prune the data set, and it is meaningful for us to prune the data set before the model is trained. Otherwise, it doesn't matter to me.
Yeah, correct. So the empirical findings, so this paper is not about the prone data set, they just provide those two findings. And this paper, the paper we are going to present today, can use their conclusion as saying that those forgotten samples, if you can calculate the forgetting score and then prone the data set, you can achieve your goal. And
During the training, or
so they claim this method is too computational expensive, so they investigate new technique to calculate the importance score before training. So this
okay,
is
maybe we can skip these ones. Maybe we can have more detailed discussion offline. You can keep going on, yeah.
Yeah, and this paper, they have 3 results. The first result is that they can prone 50% of data without the loss in test accuracy, which means there is an unequal importance of data. And the second result is that they investigate this mean loss gradient norm. So by using this score, they can identify some important score. Later, we will talk about how to calculate this mean loss gradient norm. And the third result is they investigate another score or matrix called EL2N that can identify important samples at the early training stage. And this EL2N is an approximation of mean loss gradient norm.
Okay, so this is for this paper is our paper we are discussing today, right? Okay.
And the problem setting is like this. So at first you have a training data set, follow a distribution D, and you have a finite collection of points, which we denote as S, and it has N training samples. And we have a neural network with weight W, and the output should be the logics before softmax layer, and we denoted it as FWX. And the sigma is softmax function. After that, we can output some scores, T omega X. And the loss is the cross entropy loss. And we denote the weight change as a sequence. So from W0 to WT.
These weights is all the weights in the model, right? Okay.
So yeah, so like W1 is one epoch after W0. So
okay.
And it is using the stochastic gradient descent, which means WT should be WT minus 1 minus the learning rate times the gradient change. And ST minus 1 is the samples we select to update the gradients. I think it's pretty clear.
Okay, but it's not a problem setting. So this is a
notation.
Okay, so it's a notation. So this is more context of the problem, right? But we haven't the problem definition. Right. Okay.
And then we can talk about how they calculate the grade ND score for a training sample. So basically here we wanted to calculate, suppose we remove xj from st minus 1 in the stochastic gradient descent, then what would be its influence to the other samples gradient? So
this is a question for the audience?
No.
Okay.
That means we wanted to see the influence of removing xj to other samples gradient. So next, this question can be formulated like this. So at first, we for all points x star and y star, the gradient of I think of the final score with respect to time t is this, and then the influence of removing xj should be this gradient minus the second gradient when we remove j.
And it is a bounded area, right? So it is.
So they wanted to find the upper bound of this influence.
And how do we interpret GT? X,
GT
xi,
is the
xj, yj.
GT is the gradient update.
Without removing an x.
In the t minus 1 epoch. Or without removing j, yeah.
Isn't it particular weights update? So I guess in the previous slides, the GT is given with respect to some weight, probably. Yeah. So GT is the update of the VT.
VT.
WT, sorry.
Oh,
Yeah.
WT is the update at epoch t. Weight.
The subscript of W is the epoch number, is not particular weight, right?
Yeah.
Yeah.
So,
okay.
Yeah. The WT is the weight from epoch t. Yeah.
Okay.
Yeah. So our goal is to find the upper bound of their difference.
Okay.
Yeah. So I think first the conclusion is upper bounded by the xj, the gradient of xj times a constant value. And the proof is quite simple. So when we calculate the output of the network output when given sample x and y with respect to time t, it can be expanded this by chain rule, right? And then the dwt over dt is the update gradient. So it's equal to minus learning rate times the gradient update.
I'm sorry. So how do we interpret dwt over dt?
dwt over dt, that means
The change, the gradients, the gradients of the w, the gradients of w over t.
Yeah.
And the gtxy is the gradients. And which one is the gradients? I'm feel a bit confused. The gt or wt over t. So the gradients is about the gradients of the weights, right?
Yes, we wanted to
The gradients is the gradients of the loss function of the weights.
the loss function, the weight of the gradient of loss function with respect to time t. So we write it in this form by the chain rule. And the dwt over dt is the gradient update. Right.
Okay, I got it.
Yeah, and the first term is gt x star y star. The gradient of loss with respect to the weight is gt x star y star, right?
Okay, so this is gradients on the point xy, right?
Yeah.
Okay.
So, and then you just write it as gt times the gradient of sample x star y star, and then times the times learning rate eta, and then times the gradient of xj yj. because others are canceled out by this minus.
Okay, can keep going on.
Yeah, and then we write the eta times the gradient of x star, y star as a constant c.
Okay.
So the influence of xj, removing xj to other samples gradient is upper bounded by the gradient of xj itself. So that's why the gradient, the grade ND score is the L2 norm of the gradient of xj, yj. So they use this as the influence score.
Okay. Any questions for these slides? If no questions, let's move on. Kusha, do you have any questions?
No.
Okay.
And then the second EL2N score is an approximation of grade ND. So first you can expand the gradient, the grade ND score as this form.
Can you interpret a little bit?
So the first term is the gradient with respect to the logic layer. And the second term is the gradient of logic layer with respect to the weight. So they just expand it and sum it over all class.
So can you briefly explain why calculate the grade ND is very complicated? So you just need to, since the grade ND, right, is calculated by the norm 2 or by the mode of the gradients. Isn't that easy? Yeah, isn't that easy to calculate it? Why we don't just use the grade ND, and why do we need to approximate it?
So this is even easier than the grade ND, because for the grade ND you still need one back propagation, but here I'm not sure.
And also the formula here looks a bit complicated, even if you try to interpret it a bit, and we still need to calculate. We still need to calculate the gradients,
the gradient,
right?
For any sample xy, the gradient of it should be the gradient with respect to weight w, and they just expand it by first calculate the gradient. So by the chain rule, right? First you calculate the gradient with respect to the logic layer, and then times the gradient of logic layer with respect to weight.
Okay.
This is by the chain rule, right? And the first term, the loss, the gradient with respect to the logic layer can be simplified as this. So the logic outputs minus the label.
This is a loss value. Am I right?
When you calculate the gradient, it's again equal to this form.
No, I'm saying that. So the P here is a prediction, right?
The output of the
the prediction under the case logics, right? So whatever the P here is a prediction, and YK here the label. So P minus YK is basically the loss.
It's also the gradient. So if you are interested in the detailed calculation to get this result. We can discuss this offline, but this is the result. So when you calculate the gradient with respect to the logic layer.
Okay, so assuming that it's okay, so we using the chain rule to expand the formulas, and how do we do the approximation and how to simplify the calculation?
So they assume the second term, the gradient, the logic gradient with respect to the weight are roughly orthogonal across logic. So they just ignore this term and then sum over all the difference.
So maybe I just do investigation. So how many of them really, I still have a little bit confusions. And Dr. Xiaoyan, do you have any questions for this formula?
I'm also trying to.
So
yeah,
I feel personally, I think their assumption is weird when they assume this part is orthogonal.
The point is that, so can you using a one simple sentence to describe the rationale or the approximation, and that's still, and can you go back to the previous slide? I mean, in the previous slide. Yes, in the previous slide, and so since we want to approximate the inference of removing one samples on the other gradients, right? And here we say we can calculate the gradient norm score, and it's just basically the GT XJ YJ, right? And isn't that simple to calculate this one? So why I think calculate this is complicated?
They just further.
So we just need to apply the chain rule to calculate the gradients on the gradients on XIJI, XJYJ, right? And that's all.
Yeah.
And why is complicated? And what is complexity, and how much this approximation can reduce the complexity?
So I guess this term is easier to calculate, the EL2N score.
And that is all you have. So you finish introducing the methodology.
Yeah.
Can you show the papers a little bit? Yeah, and how do they interpret the complexity? So by right, so this is just the show me the abstract. So I didn't read the abstract on detail. So could you enlarge the abstract one? So after that slide, you have finished introducing all the approach part, right? Okay.
I think in the evaluation part, they show the EL2N score is much better than grade norm.
To delete the training data. Okay, so let's forget about the technical on complexity. So I'm trying to interpret or try to rephrase the point you have conveyed. So since there's approach which allows us to calculate the triviality or non-triviality of each training samples during the early stage, as long as we have the score, which means that we can throw away those trivial samples during the training. Am I correct? So do they really do that? So if they do, how much they can throw away about the trivial samples?
Then we can look at the experiment results. Oh, sorry. Anyway, so the EL2N score is by calculating the difference between the softmax output minus and the difference with the label itself.
Okay. Anyway, the point that we don't need to calculate the gradients anymore, right? Okay.
You just
Mm.
calculate
Okay,
the
can I ask where is EL2 mean?
Expectation, right? So
error L2 norm, I think. Error. So the error is the probability, the difference between probability and the label, the one hot vector.
okay, so let's move on. You can look into the experiment.
Yeah, experiment answers two questions. The first one is how forgetting score from the empirical study paper and the gradient norm and the EL2 effect in identifying important samples. So that means if we only keep the important samples, can we preserve the test accuracy? And the second experiment is how do them negotiate the trade-off between generalization and training data set size. So basically that means if we delete the unimportant, what would happen if we delete unimportant samples? And the first row should be the experiment result for the first question. So they do it on different data sets using different model architecture.
Here is the problem is that, so maybe I raised the first, I have a question. You have mentioned that on whether a data set is important or not, is the nature of the data set instead of the nature of the model architecture, right? But for both gradient ND and the EL2N, they are calculate the score based on the loss function, which means that the score is model relevant, is more model dependent.
I think in the experiment they do an average over different multiple run, and I'm not sure.
No, I'm talking about. So assuming that we have only one model, right? We have only one model. So you can see if I have multiple models, then to make sense, I want to know the sample, the trivial sample early, right? So usually we need to prone the data set first, then we train a model. Or in these settings, we train a model for the first few epochs. We identify the trivial samples, right? So in this case, since the sample is the triviality of the samples is independent of model architecture, but the calculation is definitely the architecture dependent. And how does the paper, or from your point of view, how do you justify the approach?
Yeah, so this is a very important question. The gradient normed score is calculated at initialization. That means you don't need to train the model at all. You just initialize the model and then calculate the gradient. So it didn't involve any training. And for the
then the follow-up question is that whether the different initialization matters.
Yeah, so they, as I said, they do an average over multiple initialization.
And the average is the gradient score.
Yeah. And the EL2N score is calculated in the early training stage. That means they train the model for like 20 epoch.
And also they compare under different architecture.
Yeah, I think so.
So where's the architecture there?
I didn't.
They just show the ResNet 18, right? Oh, they have ResNet 18, ResNet 50.
But different.
But only
when they calculate the score, I think they do consider different model architecture and different initialization. But after that, you get a subset, right? And then the subset is trained on ResNet 18.
Okay, maybe we can spend some time interpret the. I think in the experiment there's only two research questions, or there's something
Yeah,
more.
only 2 research questions, but they have some different case studies.
Okay, so
But basically, they show that when they keep the important samples, the accuracy increase.
so
And
maybe you can just
the
briefly, yeah. So I just feeling that in these few rounds on your presentation seems a little bit rough. I mean the slides. So it's better for you to prepare more refined slides for a better discussion. So anyway, you can please go on to illustrate the graphs.
So yeah, in the first row, I think I just explained. So when they keep important samples,
You can start explaining x-axis, y-axis, what is the trend, what is the curve line. You just illustrate all of those.
so they have 3 baselines. The first one is non-proning, and the second one is prone randomly with the same prone rate. And then the third baseline is the forget score from the empirical study. And in the first row,
And for the forgotten scores, is the model dependent or model independent?
it should be model independent.
And how do they calculate the forget score? So you can do you read the papers? If you do, the forget score.
Yeah, actually, I shared that paper in our group before.
Okay, so okay, so what is the rationale to calculate the forget score?
So they just train the model from scratch, and then this is the ground truth, right? The sample, whether it is forgot or not.
No, so I'm asking how to calculate the forget score for a sample.
I forgot the detail, but it's either 1 or 0. I think one possibility is.
And I'm asking the rationale of calculating the 0 and 1 score.
So if you observe that if a sample first in the early training stage be correctly classified, and then in the late training stage it is wrongly classified, then it means the model forgets this.
So the calculation is still model dependent, right?
But from the empirical study, they found that those forgetting samples are stable across different model architecture.
But I'm asking the approach is still model dependent.
Oh yeah, you need a model.
So basically, all these approach, all those measurements are more dependent, despite the claim that their score will be architecture independent.
Yeah.
Okay, we can keep on introduce the diagram.
So for the second row.
No, I'm still asking the first diagram. So the first diagram is no prone, and the prone random length is a line, but the 3 measurements were have some ups and downs. Can you illustrate this phenomena?
So the non-proning is the ground truth, right? The final test accuracy. And the dashed line is the mean, and I think they consider different model architecture and consider.
And how do you interpret the score computation epoch? It is aligned with the training epoch.
Score computation. Sorry, I forget about this.
Then it's very hard to illustrate on so because this is x-axis of the diagram, right? So it's very hard to really understand what this diagram is really about.
But for the second row, the x-axis represents the fraction of data set prone, and the y-axis is final test accuracy. So the second row should be quite clear.
Okay, let's look at the second row, and what's the difference about the columns?
Columns.
Yeah.
The first column is CIFA 10 with ResNet 18. The second column is Scenic 10 with ResNet 18.
So different architectures, different data set.
Yeah.
So how do we interpret which one is the best?
The best one should be for get score, but it's very computational expensive. So I guess that should serve as a upper bound, right? And the EL2N score is better than grade and grade norm score because the blue line is above, roughly above green line.
But the question is, since EL2N is approximations for grading score, and how the approximation, and by right, it's just be a trade-off between efficiency and accuracy. So since we have already paid the cost of, so have the benefits of the efficiency, and why we will not sacrifice the accuracy. Just your formula, right? Just your formula.
EL2N actually knows more, right? Because it has a pre-train of 20 epochs, but the grade and score, we only calculate it at the initialization.
So ENS score still need to pre-train 20 epochs. So what is the model for calculating EL2N? Since the grade score is calculated as efficient initialization, so the runtime cost is just about calculate the gradients, right? So for back propagation. But for EL2N, we need to calculate 20 epochs for multiple times, if I remember correctly. So which means that it needs to calculate the forward propagations, backward propagations for the first 20 epochs. And how could it preserve its efficiency?
What do you mean by efficiency? You mean
efficiency? You're saying that EL2N is more, is less costly.
I say approximation, but I think it's more costly than the grade ND score itself. Because the EL2N is based on the grade ND score.
And what if we, so the gradient score is calculated initialization. What if we also give gradient score the first 20 epochs training?
They didn't compare this.
Yeah, I still feel that now that you have a brief overview of the paper, but frankly speaking, I do see there's a lot of details missing in this presentation.
Because it involves some mathematical proof, and I just omit them. But personally, I do look into them. So it's very difficult for me to
fully digest, or you digested it, or
I digested it. It's just if you don't look at the mathematical proof yourself, and basically there's nothing to say. They just present you a lemma, right?
Okay, so maybe I just based on your slides. So honestly, I didn't read the papers. So now just a few questions. I just feel that even if you address some of the questions, there's still some confusions in this talk. But you can see that this paper presents a very different horizon than inference function, right? It is still kind of the code inference function, but to shoot it in a different way. More like the training sample, the inference training samples on training samples. And as for the presentation Ruofan given last week, it is more like the inference functions between the tested training samples. So it is different horizons. So it's better to present it in a more intuitive and interesting way. So maybe I can come back to the question per se on 4EL2N score and whether for grading scores, we can allow it to train the first 20 epochs. Is that possible or feasible?
It's possible.
But the paper also didn't do that. What do you believe is the reason?
If they do train it for 20 epochs and then
they calculated the score as the initialization. Well, they calculate more of it, right? So they look at the initializations, calculate the gradient score. Maybe the initialization is not that accurate. And we train it for a while, right? Train it maybe 4EL2Ns, you train the first 20 epochs, and also train the 20 epochs for multiple times. Maybe at the epoch 20, gradient score have a good performance.
But the point is that they wanted to find the importance score as early as possible.
Yes, so if giving the proposal, gradient score will give the importance score no later than AEL2N because both approach takes the first 20 epochs. And also, so maybe so here. So what do we understand that in this experiment, the gradient score is less accurate because it is too efficient, or we just calculated too far because we just initialize the models multiple times and calculate score based on that. And then we do have some motivation to suspect that the authors do not fully utilize the capability of gradient score. Is that a justified claim? Is that a fair claim or not?
I think yes.
Okay, maybe let's move on. Yeah, I think there's a case study, full of the case study, right?
Yeah, and the second experiment is about identify noisy data. I guess this is very prevalent when we calculate the importance score. And they claim they do this experiment using EL2N, not grade ND, because grade ND is not as accurate as EL2N.
So this is about a case study, right? So there's no need for the baseline. Okay.
The baseline is random.
And the task is that finding the noise data. And they do not compare it with grade ND.
No.
So yeah, I think the reviewers, so I don't know how they do the rebuttals, but anyway, we can keep going.
And how did they, so the diagram is the x-axis is the fraction data set offset. So that means if it's 0.1, then it's 10%. And y-axis is final test accuracy.
And how many noise data have they injected in the data?
So on the left, we have 0% label randomized. On the right, we have 10% label randomized. And they also adopt this sliding window, which means you have a base fraction, and P is the fraction data offset. So for example, if f equals to 0.4 and P equals to 0.4, then you select and then you rank the data using the importance score, right? And then you select the top 40% to 80%. Is that clear?
Okay, so you have a range there.
And their conclusion is that they found the 500 highest score samples should be excluded from training because from left, the left diagram, you see there's a drop when we increase the fraction data offset. So that means the 5 highest score samples might be hard samples, or it can be.
Sorry, so I didn't get the point. So I do understand the diagram. So once we're removing the most important scores in the noise data, and the accuracy keep improving, right? Yeah, but for the drop at the first diagrams at the 0.6, it dropped. So what is the interpretation?
So that means because they have a sliding window, and when the fraction becomes 0.6, that means you basically include top like 60% of data, and then you will include some highest score samples.
And isn't the data is in the data
so that
ranked,
means every
the data is the data is ranked based on, or the data is removed regarding the rank of the importance, right? So for 0.0, for 0.1, it means that we remove the top 10% of the most important samples and retrain it. Right. So so come back to here. So the question is why when we remove the first 60% of the most important samples.
Let me just, for example, you have you rank the score, and this is top, and like you have a base, the window F should be here, and then you adding P% of data and reach. So each time we only keep those P% data. And if it's 0.1, then that means P equals to 10%.
And so what is the base of F?
I didn't remember.
Yeah, I see. Why the sliding window? Why they have this design? I don't get it.
The point is that the 5 highest score samples should be excluded. So that means the top score samples might not be useful. That's why they don't use that's why they use
no. It's totally a mess. So here the idea is that whether the score, the ER2 score, can help us identify the noise data.
Yeah.
Right. So this is a task.
Yeah.
And now we talk about experiment design.
Yeah.
And why there's a sliding window, why we set a base of F and the P, and why we don't just remove the first 10 or first 20% of the most important data, observe the test and accuracy. So I think that is more straightforward. And why we need a base, why we need a sliding window?
Because, so the ground truth is that the top, for example, 500 highest score samples is not useful. And if they use top, for example, top 60% of data, the result might not so good. That's why they're using a sliding window.
What do you mean by the result is not so good? And what result?
Because if you use a sliding window, then the top score samples might not be included, right?
Okay, so why we don't want to include them?
Because the result is not so good if you include them.
The result of the test and accuracy or resulting of finding.
And that's why they have this conclusion: the high score samples should be excluded. And
also, okay, so if that is the case, if that is the case, you say if the top 50 is the top 500 is not should be excluded. But how do you interpret the 0% of the label randomized, which means that for the first diagram, there's no noise data.
There's no noise data, but every
Mhm.
data set has some hard samples. The five highest score samples should be those hard samples. That's why we see a drop here, because when you increase the fraction data offset to 0.6, that means you would include the top highest score samples into your data set, right? So you see a drop in performance. And then
Okay.
when you have 10% label randomized, then
So which means that the base is set at 60%, right?
the base, you mean F?
Yes, F.
Um,
Because when you get in the
no, at
0.6,
least a 0.4, right? Because this
so what
is
do you mean by
the
at least?
fraction of data.
Okay,
that
okay. The point is 0.4. Yeah. So maybe the base is set at the 0.4.
Yeah.
Or a little bit lower, 0.35, something like
Yeah.
that. Did the paper report that?
I think I don't remember the detail, but I'm sure that when you increase it to 0.6, then you will include those highest score samples. That's why they have a drop in performance. That's the conclusion.
Okay.
And then when you have 10% label randomized, you have more noisy samples, right? So they should be the highest score samples as well. So the noisy sample would be here. And when you increase the fraction data set offset, then you will see this drop in performance because you include the noisy samples.
I get your point, but I still feel that for the experiment design and also for these AI papers, so I'm not sure how strong it is, but it do perform giving some interesting presentation. And also for these slides, I just want to say, just giving a few these bullets, it's very hard for people to follow and interpret those diagrams. So I have to be asked in a very hard way to get a big picture.
And then if you feel this way, then for the next 2 experiments, you will feel it even
Harder.
Because personally, when I read the paper, I just feel it really weird when they design the experiment like this. But anyway, let's go to the next slide. The next experiment is to compare their method with the evolution of data-dependent NTK, the neural tangent kernel. So first, what is NTK? It means the infinite with limit neural network is equivalent to a kernel called the neural tangent kernel. So that means, for example, you have a fully connected network with a hidden layer, and if the hidden layer, the neuron of the hidden layer becomes infinite width, then the neural network, the performance of neural network is equivalent to a kernel, and they call it neural tangent kernel.
So what do you mean by infinite width? So it means that it's very wide. So in other words, very wide.
The neuron of hidden layer is infinite.
The neuron of, so what do you mean by infinite? So the number of neurons or the value
of neurons. Yeah, the number of neurons become infinite. And some researchers looking into this area and investigate what is the performance of this neural tangent kernel, because it's infinite, so it has some good mathematical properties.
If it is infinite, which means in the experiment we have to give to design network in a very large number of neurons in the hidden layer, right? for example, 10 millions, 20 millions neurons in the
But
in the
that's not
layer.
the problem of this paper, but basically that's a research direction. And the performance of normal NTK is that they found the kernel gradient, or we from my personal understanding, the kernel velocity is constant during training.
What do you mean by the kernel velocity?
Which is kernel gradient. The gradient is constant.
Okay.
And
A gradient is constant, which means that they will not change during the training.
So after knowing this, they ask how is the kernel velocity or kernel gradient of different samples change during training process?
The kernel velocity is on the weights, right?
Yeah, on the weights.
It's on the
correct.
weights, so which means that you want to pick up a few
They
trivial
want
samples or important samples.
trivial.
You want to select trivial samples and you want to see whether it still keep constant.
They don't know the performance of different samples, so they do the experiments to.
Okay, so here we want to see, we anyway want to evaluate the effectiveness of the score, right? And how this score can be evaluated in these problem settings.
Yeah, so very weird, right? I read their review, the open review, and also some reviewer asked why this experiment is relevant to the evaluation of their score, and they said because the NTK is a very popular direction, and they link their score to this area, something like that.
Yeah, I think
So
even
that's why, but I also think,
even I just feel that even acceptance of neurons don't mean something.
and why they do this experiment. I checked their first paper, the first paper of the first author, and they investigate the NTK. So I think they just
Maybe you can skip this one. Maybe you can skip this one. It's really confusing. That's not worthwhile for discussion. Maybe let's move to the next slide.
And the next slide. And the next experiment is about the importance.
This is still NTK. Let's keep going on.
NTK. And is the connection of linear mode connectivity to their importance score. So the first question is, what is linear model connectivity? So from another paper, they found that the effect of mini batch randomness on the training trajectory is that when suppose we start from the same weight W, and then training using different or independent mini batches, and finally the weight will connect to the same linearly connect mode. That means your omega prime should. So if you use independent mini batches, the weight should lie in this linear line between omega and omega prime.
And omega prime is weight is converted network.
So if you use independent mini batches, then the omega prime should
should what?
That means so if you use one kind of mini batches, it will go to omega prime, and then you use another independent mini batches, it might go to, for example, omega prime prime. Then the omega prime and omega prime prime should lie in a linear connected line.
On the hyperspace.
Oh yeah, on the hyperspace. So this is the linear model connectivity from another paper. So mathematically, the trajectory should not be diverge from the linear.
You mean too away from the linear, yeah. And also this might indicate that whatever we choosing shuffle the mini batch, we'll always arrive the
A linear
position,
connect.
always arrive the position of omega prime or W prime.
Yeah,
Is that
correct. And then the experiment design is like this. So first you have a same start point omega, and then they choose different subset to train the model. One is with the minimum EL2N value, the subset, and then another one is the maximum EL2N value.
so you evaluate the distance from W, or the positions between the W in the segment between W and W prime to see. So if it is a trivial samples, it moves slower, but if the informative samples, it move faster. In that case,
so if you use the maximum value samples, it would go far away from that linear mode, right? Because the error, the y-axis is the error barrier. If you use the minimum score value samples to train the model, then it would fall into that linear mode, fall into that linear
segment.
segments.
I still feel a bit confused about the
That
segment
means
definition.
if you use the maximum score samples to retrain your model, then your model would change drastically. So I'm not sure whether you remember when we tried to find the motivated example of time-based, we tried to train the model using some test samples that are wrongly classified, and my result is the model changed drastically, like the accuracy dropped. So I think that somehow agree with the results.
No, I'm talking about the segment. I understand. So the more informative samples we feed into models, the more drastic or radical change on the network. But I'm asking about the line segment between omega and omega prime, right? And so which means that, so if I interpret it in a correct way, so the line between omega and omega prime means that the model have the same behavior. So anyway, so giving this experiment, I'm not sure it's problem of the integrated paper, or maybe we don't find a good paper. That is also the case. So you can see the more informative the samples, if their approach is effective, we can find the most informative samples. So the performance is away from the distance away from the line segment, right? So which means the model have a different behavior. And if we find the trivial samples and the line is very close to the segment between W and W prime, so which means that every point, which means every network line on the line segment share similar behavior. Is that interpretations or not? You don't know, or?
I don't know, because the only conclusion from the paper, they only claim that examples with high score and low score behave differently.
Yeah, so let's talk about another experience. Suppose we are the one to design experiment, we definitely not go in this direction, right? We will not have this experiment set up. We're just saying that when we're removing a portion of the training data, whether we can achieve the sense semantics, right? The model can preserve the sense semantics. The semantics we can using different measurement for the semantics. For example, the testing accuracy is one way of semantics, or maybe the trained model share the same vulnerability, right? This is another kind of semantics, or maybe the model both model can be used to distill a similar smaller model, right? This is another kind of semantics. If we are the one to do this, we just want to say that whether the smaller data set allow us to achieve a model with exactly or with similar behaviors, right? Yeah, this experience feel a bit weird. Okay, so is that the end of the presentation? So,
Yeah, yeah.
maybe my last question is that how do you evaluate their approach design? I understand that they start from the forget score, right? So forget score, then the methodology is developed from forget score to the grade D and ND, right? So they further improve the grade ND into EN to
Yeah,
EL to N, right? So what do you think about the whether you believe their approach is whether convincing or not?
For grade ND, it seems reasonable, but EL to N is not. I mean, their justification is not that convincing. Although I do feel the difference between probability and one-hot vector should be one way to evaluate how important the sample is, but their justification is not convincing.
Yeah, but they have published in Europe, right?
Yeah,
Last year.
and the experiment also seems.
Yeah, I just feel
The
that
case study
the
seems
more
really
the
weird.
more we look into the papers, the more confident we say that even the Europe's papers, sometimes it is good for the writing, right? They introduce a lot of mathematic inference. Maybe we are still not that getting to that area, but just for an experimental design, we do have a lot of questions for that. Yeah, so
You are also raised the same question.
yes, so I think when we have these discussions, we are more likely in the process of demystify the venues we have no publication there. So for example, some venues like Neurops, which has a very good reputations, but not every paper on that venues is a strong one, right? So we should have the confidence to targeting for these venues. All right, so so maybe I can have a brief conclusion for that. And so anyway, this approach is a way for us to evaluate the inference between the training points. So as long as a training point or training samples is not non-trivial, we have a very good reason to remove sense, which can not only improve the training efficiency, but also allow us to apply maybe some separate of concern strategy, right? So when we want to fit in the model, we want the model so the smaller number of the sample there, the easier the model can fit those samples instead of looking to a lot of noise data. And if we can investigate more of the training points, we can find the noise data, we can find the redundant data, we can have a lot of way to improve so we do have a lot of way to improve the training efficiency. But if we look in the data, remove some unnecessary data, definitely it also can be considered a way to further optimize the training efficiency. I think that is very interesting to investigate, despite that we have some confusions on the paper. Yeah, if you are really interested, you can also maybe have an offline discussion with Xianglin, or you can revisit the papers and to raise another offline discussions. And yeah, that will be definitely welcome. And for now, I think we reached the end of the presentation. Are there any questions for this topic? Okay, if there's no questions, let's call it a day then. Thanks, Xianglin, again for the presentation. Okay, bye.